Hello everyone, good day, good morning, good afternoon, and this will be our third topic for our meteorology class, and we're gonna talk about water and earth. The topic is all about the humidity, condensation, and fog. It circles around this main topic. And again, we're still following the two books here, as you can see, The Essentials of Meteorology by Adams and The Atmosphere: An Introduction to Meteorology by Lutkins et al. So we're on the chapter 4 of this book, and for the content, first, we're going to talk about the circulation of water in the atmosphere, and then we're also going to see, well, sort of a review of the water's changes of state, because I'm sure you're already familiar with this, and then also the humidity, which we've already mentioned in the previous lecture, the water vapor in the air, but we're going to talk more closely in this topic in today's lecture. So another will be we will also discuss the dew and frost and the fog. So for the water in the atmosphere, I'm sure you've already seen this um, figure, because this photograph, I've already presented this in the previous lecture. It's just to show the hydrologic cycle. So it is said that the continuous exchange of water among the oceans, the atmosphere, and the continents, it is called the hydrologic cycle. It is the cycle or the movement of water in between the ocean, the atmosphere, and the continents. So it involves a different, in the arrows, it shows the different processes from evaporation. I mean, from the ocean, the water evaporates to the atmosphere, to the clouds, and then it starts to precipitate, forms precipitation, and goes back to the ground. And then there's infiltration, and of course the runoff towards the ocean again. And there's another evaporation and transpiration process. But we're gonna check into this in the next slides. So it's just to show the general cycle of the water movement. And so first we're going to talk about the unique properties of water, since water is the main topic, or the main idea of this topic. First unique property of water is that water in general is the only liquid found at Earth's surface in large quantities. So we all are aware that our Earth is actually composed of a larger volume of water compared to the land mass. So that is one unique property of water. And also, water is readily converted from one state of matter to another. It can convert from solid to liquid, liquid to gas, or solid to gas. It's convertible from one state of matter to another. And water is also more dense in its solid phase. Like the ice, it's denser when you compare the density to the liquid phase, the liquid water. So not all of you may know this, but now you should remember that ice is more dense or denser than the liquid water. And the last unique property of water is that water has a high heat capacity. That means changing its temperature that requires considerable amount of energy. And so these these unique properties are largely a result of the water's ability to form hydrogen bonds. Because if you recall, water is composed of hydrogen and oxygen, H2O. So these unique properties is actually responsible by the hydrogen bonds. The unique properties are largely a result of water's ability to form the hydrogen bonds. And so, as the definition, what is hydrogen bonds? These actually, hydrogen bonds are the attractive forces that exist between hydrogen atoms in one water molecule and oxygen atoms of any other water molecule. And so, this hydrogen bond is actually the one holding water molecules together to form the solid we recognize or we call as ice. For example, in this figure, it shows here in the upper part, this is the figure A, the water molecule. It has one oxygen atom and two hydrogen atoms. So below this are the hydrogen bonding. What I mean is the water molecules that are bond with the hydrogen bonding. So as you can see, the water molecules are joined together. These lines are the hydrogen bonds joined together by hydrogen bonds. And it loosely bond a hydrogen atom. For example, it loosely bond a hydrogen atom to an oxygen atom of another water molecule. So in this, another oxygen atom is bonded to a hydrogen atom in another water molecule. And so below that is, you can see the crystalline structure of ice. So the water solid phase has a crystalline structure because it's called crystalline structure because it's a rigid structure. That's why ice has a lesser density than the liquid form, because if you can see, it's more rigid and it has more space because it has become more compact compared to the liquid phase of the water. And so uh, actually water heats up and cools down more slowly than most other common substances because of these hydrogen bonds. And large water bodies tend to moderate temperature. Um, and hydrogen bonds also has something to do with it because water's heat capacity, for example, when water is heated, some of the energy is used to break the hydrogen bonds rather than to increase the molecular motion. So if you remember that the increase in molecular motion, average molecular motion, it corresponds to an increase in temperature. So under a similar condition, water heats up and cools down more slowly most than most other common substances, liquid substances, or just in general compared to other common substances. Water heats up or cools down more slowly because the heat energy is used first to break the hydrogen bonds rather than before it can increase its temperature. And when water changes state, the hydrogen bonds either form or are broken. So it's not just breaking the hydrogen bonds, but also it can form the hydrogen bonds when it changes from one state to another. So now we're gonna proceed to the different states of the process of changing the state of water: evaporation, condensation, sublimation, and deposition. So as you can see in this figure, there in this part is the solid ice, where the water molecules in ice are bonded together in a configuration that has lots of empty space, which accounts for ice being less dense than the water, as what I have mentioned in the previous slide. Because of this hydrogen bond, the bond or the structure is more rigid, that it has more empty space. That's why it's denser. It is, I mean, not denser, but less dense compared to the liquid structure of the water. And from solid, it can actually go to gas. This process is what we call sublimation, and so on. From gas to solid, this is deposition, and from solid to liquid, this is, yeah, basically just a review, melting, and then liquid to gas is evaporation, and the opposite for that is condensation and then freezing. So if you can see that it has this label that about 680 calories absorbed for sublimation and 680 calories released for deposition. That is because the change of state of water involves an exchange of energy. So the heat involved when water changes state is measured in units called calories. And 1 calorie is amount of one energy required to raise the temperature of 1 gram of water 1 degree Celsius. So the melting, as what you can see in here, it's 80 calories absorbed. 1 gram of ice requires 80 calories or 334 joules to be able to melt 1 gram of ice. So this energy, actually, this amount of energy required is called or termed latent heat of melting. So if you remember again the latent heat, it's called latent heat because it's hidden heat. You cannot see it, but this is the energy required for the process of changing the water state. And then another is for freezing. It's just the opposite of melting. So it releases 80 calories, 80 calories per gram to the environment as the latent heat of fusion. So if for melting, the energy is called latent heat of melting. For freezing, it's called the latent heat of fusion, the energy that is used or the release energy. Again, this is the same figure. The 6-phase changes of water are evaporation, condensation, freezing, melting, deposition, and sublimation. So we've already mentioned for the evaporation, for the melting and freezing rather. And here we also have this latent heat for vaporization. So for the evaporation, the latent heat, it varies from 600 calories per gram of water at 0 degrees Celsius to 540 calories per gram at 100 degrees Celsius. That's how it goes to the energy that we need to 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 make the water evaporate. And for the condensation, the water vapor molecules release energy. That's what we call the latent heat of condensation. So it's just everything is just a latent heat, but each process or each phase has this latent heat involved. So the latent heat of condensation is what we call for the condensation process. So it's the same amount equivalent to what was absorbed during the evaporation. So since evaporation and condensation is the opposite to one another, so it's just basically just the same amount of energy needed. And so sublimation, I think this is the least familiar, the least the process that you're least familiar with, I think, because it's very common to have the evaporation, condensation, but the sublimation is a bit different. But this is the conversion of a solid. The solid is directly converted to gas without passing through the liquid state, without melting. So the example you may observe uh, include, for example, the gradual shrinkage of unused ice cubes in a freezer, because the the phase or the ice from solid, it just gradually shrink, and then some of it just turn to gases, if you notice that in your freezer. So also another example for sublimation is the rapid conversion of dry ice. I'm not sure if you're familiar with the frozen carbon dioxide, but it's the dry ice. Uh, the rapid conversion of dry ice to wispy clouds that quickly disappear. This is what happens in nature, like in the environment. So this is how sublimation occurs. And the opposite of sublimation is the deposition. This is the conversion of a water vapor directly to become solid. So the example for this is, let's see, here, the frost on a window pane. This is an example of a deposition. So another is when water vapor deposited as ice in a solid object such as grass, for example, in days that it's really cold. So there are deposition, or the water vapor that is deposited as ice on the grass. Is what, I don't know if you've already witnessed that or if you've seen that in person, but these happens also in real life by nature and environment. So in this picture, the B is the example of the deposition, but for this A is just an example of condensation, which we have already like passed in the previous slide. We've already talked about, I've mentioned about this, the condensation of water vapor. And in this picture, it generates the phenomena such as dew, clouds, and fog, which we're going to talk about later on. And so humidity. Humidity, if you can still remember, I think I gave a quick definition of humidity before in a previous topic, which is the water vapor in the air. So water vapor is said to be the primary source of energy, which is the latent heat, for the formation of weather systems like the thunderstorms, tornadoes, and hurricanes. So as what you can see, there are five ways that the meteorologists use to express water vapor, the water vapor content of the air. First is the absolute humidity. Next is the mixing ratio. Third is we have vapor pressure. And then we also have relative humidity. And lastly, we have the dew point. So we're going to tackle this one by one. And this is just, in this picture, is just an illustration of, for example, of the water vapor. For example, here, The circle is general. In general, it illustrates, for example, a parcel of air, and the blue ones illustrates nitrogen, and the oxygen is the red one, and then the water vapor is combined with the water, the hydrogen, and the oxygen. So that's the water in the form of water vapor. So, so the first expression of humidity is what we call the absolute humidity. So the absolute humidity is the mass of water vapor in a given volume of air. So for example, just focus in this first circle. This circle is the volume of air. And the absolute humidity is the mass of the water vapor. So the water vapor is inside this volume of air, and this one parcel of air is what we call the volume of air. So as air actually is moving from one place to another, it also changes its pressure and the temperature. And when it's moving and it's changing the pressure and the temperature, it also changes the volume. So this volume of air changes, and the absolute humidity also changes, even if actually the water vapor is not changing, is not added, or there is no addition or removal of water vapor. So in this situation, that's why it's difficult to monitor the water vapor content of a moving mass of air when using this type of humidity index, the absolute humidity. So therefore, scientists or meteorologists generally, they prefer to use the mixing ratio to express the water vapor content of the air, because mixing ratio is not affected by changes in pressure as the parcel of air rises and expands. So what is mixing ratio? Mixing ratio is the mass of water vapor in a unit of air compared to the remaining mass of dry air. So because it's this mixing ratio, it is measured in units of mass, usually grams per kilogram. Then the mixing ratio is not affected by the changes in pressure or temperature. For example, in this figure, as what you can see below here is the mixing ratio, and above is the absolute humidity. You can see that when the air expands, when the air rises, it expands, so that the volume also increases. But below, it's the smaller volume, and the above is the larger volume of air. And that means the size of parcel from 1 cubic meter, it has now become to 2 cubic meters. So if you check the absolute humidity of this air, of this volume of air, the absolute humidity in a smaller parcel is 20 grams per cubic meter. And in this larger parcel, in this larger volume of air, it's 10 grams per cubic meter. So there is a difference. That's why it's difficult to track the humidity when you're using the absolute humidity because of the changing volume of air. But with the mixing ratio, it stays the same. It's only 20 grams per kilogram. It's not affected by the change in pressure or the change in temperature. So the third expression, or the index of humidity, is the vapor pressure. Now, we will know what is vapor pressure and what is its relation to saturation. So vapor pressure is defined as that part of the total atmospheric pressure attributable to its water vapor content. So, okay, check this figure. In this first, in the upper left, you can see that this is the initial condition. There is dry air above and water below. For example, imagine this, that you have a flask or a water bottle, right? Your water bottle is not that full, and there is an empty, like dry air above. Like when you close the water bottle, there is an empty space above. So that is the dry air here, and the water is there. And this actually creates like evaporation for in this figure B. There is evaporation that happens. So more water molecules are evaporating, and there it the evaporation generates measurable amount of vapor pressure. So this is what you call the vapor pressure, that part of the total atmospheric pressure attributable to its water vapor content. So in the figure C, you can see that as evaporation goes higher, there is also a condensation that is happening as more molecules escape from the water surface. So the steadily increasing vapor pressure forces an increasing number of molecules to return to liquid. So there is amount of evaporation and then the condensation that happens. Eventually, the number of water vapor molecules returning to the surface will balance the number of the water molecules that are leaving. And then this point, at which point the air is said to be saturated. So now it will reach a point which the air is said to have the equilibrium. So that's what we call the saturation of the vapor pressure. So, and in this D figure, when the container is heated from, if you can see in this figure, this is A, B, C, D. The D figure, when the container is heated from the bottom, like 20 degrees Celsius to 30 degrees Celsius, the temperature is here written. The rate of evaporation actually increases, causing the vapor pressure to increase until the new balance is reached. So even if there's already an equilibrium that is reached, but when there is heat, there would be a new balance to reach, because the rate of evaporation increases and then more vapor pressure. That means the new balance is reached. So when the air is saturated, this is what we call the saturation vapor pressure, because the pressure exerted by the motion of the water vapor molecules is what we call the saturation vapor pressure. I hope you can imagine it in in a water bottle, that the empty space above, actually, because of the water, there is an evaporation that happens. There's a vapor pressure. Okay, let me give you an example. For example, when you open a bottle of Coke, there is a pressure for that. That's because, well, it's not water, but it's generally like liquid. The, it follows the same mechanism, I guess. So in nature, the gravity is what represents as the lead. So in the water bottle, there is a lead, right? There is a cover, there is a cup. So that prevents the water vapor from escaping. So that's why there is a dry air on top of it. So in general, in the environment, that lead, this cup is just a representation for the gravity in the environment. So the gravity is what prevents the water vapor and other gases from escaping into space. So with a container example, the water molecules are constantly evaporating from liquid surfaces, such as, for example, the lakes. This is what the the situation happens in in nature, natural environment. So we've mentioned the balance is achieved, the equilibrium, the saturation, but in natural environment, the balance is not always achieved because more often than not, more water molecules are leaving the surface of a water puddle than arriving. And so we're moving on to the relative humidity. This is the fourth humidity index, how you express the water vapor or measure the water vapor. So what is relative humidity? Is the ratio of an air's actual water vapor content compared with the amount of water vapor required for saturation at the temperature and pressure. So in its formula, this is how you do it, the mixing ratio divided by the saturation mixing ratio. So relative humidity is the actual water vapor in the air over the maximum water vapor in the air that can hold. What does it mean? The maximum water vapor in the air can hold, that involves the temperature and pressure. So it's not always the case that the air with higher relative humidity, we think that if it has a higher relative humidity, then it has a greater water vapor content compared with a lower relative humidity, but it's not always the case because very cold places are also very dry. So the low water vapor content of a frigid air, even when saturated, uh, it helps explain why the cold areas or the Arctic areas receive only small amounts of precipitation and are referred to as the polar deserts. So the water vapor content of cold air is low, even compared to some hot regions. So yeah, to make it more clear, this relative humidity, it can change in two ways. So the change of relative humidity, it changes when the water vapor is added to or removed from the atmosphere. And also, it changes with varying temperature. It varies with temperature. So relative humidity is based on the air's water vapor content as well as the amount of moisture the amount of moisture required for saturation. And because the amount of moisture required for saturation is a function of air temperature, that's why this relative humidity also changes, depends on the temperature. Okay, just to give more illustration in this. Okay, so apparently the increasing moisture or decreasing temperature both result in an increasing in relative humidity. So let's see in this figure, we have A, B, and C. First is the 5 grams of water vapor. This is the initial condition. So the next one, we have added 5 grams of water vapor. So from 5 grams here in the first picture, it has now become 10 grams of water vapor. And in the third picture, there is an addition of 10 grams of water vapor. Now it has become 20 grams of water vapor. So as what is mentioned, as what you can see, is what you can read, and what I've mentioned, that the increasing moisture, that means there is an additional water vapor. That is the moisture that we refer in here. And with increasing moisture, there is also an increase in relative humidity. You can see that the temperature stays the same, but there is an increasing moisture. Therefore, the relative humidity is increasing. And in another picture, here, in the right side, you can see that there is a varying or decreasing temperature. The temperature here is now decreasing from 25 degrees, 15 degrees to 5 degrees Celsius. So when the water vapor content or the mixing ratio remains constant, unlike in the previous one that we added, there is an increasing moisture, so there is an increasing relative humidity. But in here, if the vapor content remain constant, and the relative humidity will change when the air temperature increases or decreases. For example, in this is decreases. So in this example, when the temperature of the air in the flask, this flask that you can see, was lowered from 25 degrees in A, from 25 degrees in A to 15 degrees in B, the relative humidity increased from 50 to 100%. Here is the relative humidity, 50 to 100%, because it decreases the temperature. And so the further cooling, which the decrease of temperature from 15 degrees Celsius to 5 degrees Celsius in here, causes 1/2 of the water vapor to condense. If you see, there is from 10 grams and 10 grams, even if you decrease the temperature, the moisture or the water vapor is constant. And then in here, the further cooling, it causes this water vapor to decrease. I mean, to condense. The 5 grams of H2O now has become liquid. You see, in this 10 grams of water vapor, it's empty. It's just the water vapor. And now, because of the cooling, The cooling of the temperature has made this water vapor condensed and become liquid. So there is no reason to assume that cooling would cease or would stop the moment the air reached saturation. So what happens when the air is cooled below the temperature at which saturation occurs, as what you can see in the last figure. So this illustrates that it becomes the water vapor becomes condensed. It becomes liquid. So it's typically the same in the environment. Because this flask originally contained 10 grams of water vapor, and then 5 grams of water vapor will condense to form the liquid droplets that collect on the walls of the container. So in the meantime, the relative humidity of the air inside remains at 100%. So the relative humidity has already increased at 15 degrees. So when you decrease the temperature, the relative humidity has already decreased. And then the further cooling, actually, it just made the water vapor condensed, but the relative humidity is still the same. So in nature, this is an important illustration that when saturated air cools on the atmosphere, some of the water vapor condenses. So it condensed to form clouds, dew, fog. So we conclude that when the water vapor remain constant, the water vapor content remains constant. A decrease in temperature results in an increase in relative humidity, as what is illustrated here from A to B. Decrease in temperature, increase in relative humidity. And conversely, an increase in temperature results in decrease in relative humidity. So it's just the opposite. If you increase the temperature, then the relative humidity is decreased. That means the air becomes drier if you increase the temperature. And there is more moisture in the air if you decrease the temperature. So that's what the relative humidity is all about. And to show you the natural changes in relative humidity, the natural phenomenon where you can observe in the environment. So there are 3 major ways that air temperature change to cause the change in relative humidity. So, this air temperature change over relative short time includes, for example, the daily changes in temperature due to the daylight or the nighttime, and also the temperature changes that result when air moves horizontally from one location to another. So there is a cooling of it depends the horizontal movement of the air, cooling or the increasing of temperature. And then the temperature changes caused when air moves vertically in the atmosphere, not just the horizontal movement of the air, but also the vertical movement of the air. It also changes the temperature, and that way, since relative humidity varies with the temperature, then it also changes the relative humidity. It is shown here in the graph. For example, if this is just an example in one place, in here, in the vertical axis, you can find the temperature in the left side and the relative humidity in the right side. And in the horizontal axis, this is the time, 12 midnight, 6 a.m., noon, and 6 p.m., and 12 again. So there is the lowest temperature here in the morning. So when the temperature is low, there is the highest relative humidity. So again, when you lower the temperature, there is more humidity in the air, more vapor, more water vapor in the air. And then the lowest relative humidity here at night or in the evening, because that's because in the evening we have the highest temperature. So it's just like that, the relative humidity. Okay, now we're gonna move on to the dew point. I think you've already heard what is morning dew. Morning dew. So this dew point is another index to express the humidity. We've already discussed the relative humidity, the vapor pressure, the mixing ratio, and the absolute humidity. Now this is the fifth expression, or the fifth index to express the humidity or the water vapor in the air. So what is a dew point? This is the temperature at which water vapor begins to condense. So in other words, the temperature at which air reaches saturation, and then it begins to condense. So the term dew point, it comes from the fact that during nighttime, the objects near the ground, for example, the grass, so near the ground is often cool. So when these objects cool below the dew point temperature, and they become coated with this what we call the dew. So that's why this is termed as dew point, the temperature where the water vapor begins to condense. So it begins to condense at this temperature, then therefore it is directly related to actual moisture content of a parcel of air. And this is the example of the dew, morning dew. So this dew actually happens when the air is cooled below its dew point temperature. If the dew point is above freezing. Because if the dew point temperature is below freezing, then it's not the dew or fog that occurs, but the frost. So here you encounter two things, the dew and the frost. So you are familiar, I think, with the dew, morning dew, and the frost when everything starts to freeze, this dew. And when the dew point temperature is below freezing, or the 32 degrees Fahrenheit, that's when frost occurs. So after we've talked about the humidity and the dew and the frost, we have also the fog. and we're going to discuss the different types. So fog is a cloud with its base at or very near the ground. The base is at the ground or very near the ground. So it forms in two ways. Either one of these two. First, by cooling, when the temperature of a layer of air in contact with the ground falls below its dew point, then condensation happens that produces fog. As what I've mentioned, it's either the dew or the fog. And yeah, fog could also form when the air is cooled below its saturation point or below the dew point. And another way of fog formation is the evaporation and mixing. So this evaporation and mixing happens when the water vapor is added to the air by evaporation and the moist air mixes with relatively dry air. So evaporation fogs is the result of evaporation of water that is warmer than the surrounding air. So it includes um, it includes steam fog and precipitation because there are different types of fogs for the fogs that is formed by cooling. There is radiation fog, advection fog, and upslope fog. And for the fog that is formed by the evaporation and mixing, we have the steam fog and the frontal precipitation fog. So we're gonna go first with this radiation, advection, and upslope that is formed by cooling. So what you can see in this one is the radiation fog. In this picture, this is the satellite image of a dense fog. So this early morning radiation fog was responsible for actually several car accidents. It can be harmful, as what you can see in the second picture, in the bigger picture B, that the radiation fog can make a morning commute quite hazardous. So this radiation fog is a result from the radiation cooling of the ground and the adjacent air. So it is a nighttime phenomenon that requires clear skies, high relative humidity, and relative light wind. So under the clear skies, the ground and the air immediately, I mean, when you have the clear skies, the ground and the air above cools rapidly. So because of the high relative humidity, a small amount of cooling lowers the temperature to the dew point. So that's why this phenomenon occurs and it forms the radiation fog during the nighttime with clear skies. Next to it is the advection fog. So this advection fog, as you can see in this meteorologist sketch, there is a moist air that is cooled by cold water below that forms the fog. So that's why it's called advection fog. It is formed when warm moist air moves over a cool surface. So this warm moist air blows over a cold surface, then it becomes chilled by contact with a cold surface, the cold surface below. So if cooling is sufficient, the result will be a blanket of fog. Then this is what you can see in the picture. And the term advection refers to air moving horizontally. That's why it's called advection fog. Another is the upslope fog. So it's, as you can see, it's the fog that is formed when relatively humid air moves up sloping the terrain. So when you can see a fog that is sloping the terrain like this in the mountains, that is what we call the upslope fog. So those are the fog that is formed by. So there is another way, as what I've said, to form the fog when the saturation occurs primarily because of addition of water vapor to air. The resulting fogs is this. This is one of the evaporation fogs, the steam fog. So this image shows the steam fog rising from Sierra Blanca Lake in Arizona. Because this steam fog occurs in the fall when cool air flows over a comparatively warm water body. So the steam fog happens over a warm water body. So this is a common occurrence. This is very common occurrence over lakes and rivers during clear, crisp mornings in autumn or in fall, when the water is still relatively warm but the air is comparatively cold. Because when this cool, unsaturated air moves over a warm water body, then enough moisture may evaporate to saturate the air directly above. Then it generates the layer of steam fogs. So these added moisture and energy, this often makes the saturated air buoyant. It rises, so it's buoyant enough to cause it to rise, and that's why it's foggy. And because these fogs or this foggy air looks like steam, for example, in your coffee, there's a steam coming from that. That's why it's called the steam fog. It's the steam. We all know what is steam in general. So this fog normally occurs over a water body. So another type of fog that is formed with the addition of water vapor to air is the frontal precipitation fog. So the frontal precipitation fog is actually um, when there's a frontal boundaries where a warm, moist air mass is forced to rise over cooler, drier air below. So then this drier air below generates frontal fog or frontal precipitation fog. So the foggy conditions result because the raindrops falling from relatively warm air that is the warm air that has risen. So this warm air that has risen over the cooler air, it has produced the raindrops falling. And so because the raindrops falling from this relatively warm air above the frontal surface evaporate in the cooler air below, then these cause the cooler air to become saturated. This frontal fog, which can be quite thick, is common on cool days during extended periods of light rainfall. So actually, what you can see in this is it looks just like a cloud, because physically clouds and fogs, they their appearance and the structure are the same. The difference is only the method of formation. So the essential difference between fogs and clouds is how they are formed and also the place where they are formed. But basically, in structure and in appearance, physically, fog and clouds are the same. And to sum up, in summary, these are the important, like some points that you should remember. In general, the unending circulation of Earth's water supply is called hydrologic cycle, and the water has unique properties and it can change from one state of matter to another. And when the air is saturated, the pressure exerted by the water vapor is called the saturation vapor pressure. And relative humidity, or the relative humidity, can change when the air's water vapor content changes or when the air temperature changes. And then dew, frost, or the frozen dew, generally form on clear nights when the temperature of objects on the surface cools below the air's dew point temperature. And the visible white frost forms in saturated air when the air temperature is at below freezing. So, lastly, fog is generally considered an atmospheric hazard, is a cloud with its base at or very near the ground. So the base is at the ground or very near the ground for the fog, and it's considered an atmospheric hazard. So that would be all for today. So thank you so much for your attention.